So good evening to one and all. Coming to the realization of the discrete time systems. So there are two types of the realizations of the discrete time systems. First one is the recursive realizations. Recursive realization. So or which is also called as a IAR, infinite impulse response filters realization. And the second type is non-recursive realization. One is recursive, non-recursive realization, which is also called as the FIR systems or FIR filters realization, which is also called as the finite impulse response systems realization. Realization is nothing but a implementation or physical existence of the discrete time systems. Nothing but a for analog or continuous time systems, how we can construct the continuous time systems by using active and passive devices like resistor, capacitors, inductors, ICs. By assembling all those elements with some proper structure, then we can get the continuous time system which produces some response for a given input. Like an example is amplifier, where that amplifier is required to one BC107B transistor and two or 2 to 4 resistors and 3 capacitors, like which will be acts as one is a blocking capacitor, second one is the coupling and emitter bypass capacitor, and source voltage source, that is VCC, and input one sinusoidal signal like this one. So you can assembling all those resistors and capacitors and transistor with a fixed biasing circuit, where that circuit is called as amplifier, nothing but which is a continuous time systems which is made up of the active and passive components. To assemble all those components in a proper way with some predefined rule, which is called as the amplifier, which amplifies the input signal. So this is the about the concept of the continuous time system. So there is a physical existence is there in the continuous time systems by arranging the all the active and passive elements in a proper manner to produce some output or some predefined output or some desirable output or some useful output. In similar way, for how we can construct the discrete time systems, that concept is nothing but a realization concept. Generally, in case of the recursive realization, what is meant by the first recursive means, all of you know that in the case of the first chapter, recursive is nothing but the system present output y of n is always depends upon the present input, comma, past input as well as the past outputs also. Feedback is existed here. So this is the recursive system. Whereas in case of the non-recursive realization, or in case of the non-recursive systems, the system present output y of n is always function of only present and past inputs. No need of depends upon the past outputs. If it is a depends upon the past output, that is a recursive. Otherwise, it is called as the non-recursive. So realization, generally these recursive systems are nothing but these are the IIR, infinite impulse systems, whereas these are the called as the finite impulse response systems, FIR systems. Okay. Now coming to this one, what are the methods are used for realization purpose? Before that, what are the components are used, or what are the elements? For in case of the discrete continuous time systems, there is active and passive elements. In a similar way, for discrete systems, what are the components or elements are used for realization purpose? The first one is adder. So I think all of you know this one. Adder nothing but a 2 input adder, x1 of n plus x2 of n. To reduce the complexity in the designing, generally we are using the 2 input adder. Next, the second element is used for scalar multiplier. Second element or second device which is used for realization purpose is scalar multiplier, nothing but a x of n is multiplied by the some scaling device or with a value, and the output is nothing but a into x of n. So this is about the scalar multiplier. And the third important element for the discrete time system is delay element or storage element. Delay element or storage element. So nothing but suppose if x of n is applied to the delay element, generally that delay is defined by z inverse. So output is nothing but input is delayed by the 1 unit, nothing but x of n minus 1. Suppose I want to delay the input by 2 units. No need to use the z power of minus 2. That is a complex one. First we use the z power minus 1. Again the output is one more time we can apply for z inverse, where the output is x of n minus 2. So this is the concept of the realization, where the elements that are used for realization purpose for discrete time systems is adder, scalar multiplier, delay element or storage element, which stores the 1 bit or 1 amount will be stored. The information will be stored in the z inverse by 1 unit amount of time. 1 unit amount of time. So these are the elements or components that are used for realization of the discrete time system. This is about the introduction related to the realization of the discrete time systems. But two types. One is the recursive realization for IR, that is nothing but IR filters realization or IR systems realization. Second one is the non-recursive realization, which is also called as the FIR systems or FIR systems realization. So first of all, what is meant by the recursive means the present output is always depends upon the present input, past input as well as the past output. Similarly, for non-recursive realization is nothing but it depends upon the present and past input. So these are the elements that are used for realization purpose. So I can give a small example here. So how the general realization is there. Suppose y of n is equal to y of n minus 1 plus 2 into x of n plus 2 into x of n minus 1, suppose. So how can implement this one means, so first x of n is there, which will be delayed by the 1 unit z inverse. So I will go for only okay. So what is the z inverse output? X of n minus 1, which is scaled by the how much value? 2. And here how much scaling value? 2. So output of after the scaling, the result is 2 into x of n. Here output is 2 into x of n minus 1. Both are added here. So in the expression, what is the expression? A 2 into x of n plus 2 into x of n minus 1. And this output is nothing but a which will be added to the y of n. So here output is y of n and which will be delayed by the 1 unit. How much 1 unit? So here y of n minus 1 and which is scaled by the how much value here? 1 only. So 1 into y of n minus, which will be added to the previous value. So that here one more adder we required. That's it. So here we can get the y of n minus 1 plus 2 into x of n minus 1, which will be added with the plus 2 into x of n minus 1. So this is the realization structure. So in the real time, here this complete system, here this is called as the discrete time system. This is called as, sorry, bro. So up to this point now. So in the real time, this is called as the discrete time system. This is called as the discrete time section. Here input is x of n, output is y of n. Clearly observe it now. This is the one example for the structure. How the real time structure or real time realization technique is existed. So this is the, today we will discuss about these concepts now. అందులో in that you can discuss about the first one, realization of the recursive realization or recursive realization or IIR systems realization. IIR systems or IIR filters, IIR systems realization. What are the methods are used for IIR systems realizations? Means totally 4 types according to the syllabus. One is the direct form 1, second one is direct form 2, second one is direct form 2, and third one is the cascaded realization. Sir, why these 4 types of the realization? Very simple logic, depending upon the availability of the area on the chip. Depending upon the area available on the motherboard or on the chip, we can choose the realization technique. That's a very simple technique. Okay, so one is the direct form 1, direct form 2, cascaded and parallel forms. So one by one we discuss about the one by one technique. First we go for the first technique is direct form 1 realization. Very simple logic and simple realization. Directly we can implement. The name itself indicates direct form 1, nothing but directly we implement the difference equation. Whatever the difference equation is mentioned here, completely they execute the difference equation directly. So before that, the system difference equation, the nth order, the system difference equation, that is LCCDE, is given by y of n is equal to minus summation k is equal to 1 to n ak into y of n minus k plus summation k is equal to 0 to m bk into x of n minus k. This is the nth order difference equation for recursive systems or IIR systems. For recursive systems or IIR systems, just apply the Z transformations. Apply the Z transformation. Apply the Z transformation on both sides. We can get the y of z is equal to minus summation k is equal to 1 to n ak into y of z into z power minus k plus summation k is equal to 0 to m bk into x of z into z power minus k. I think all of you know this, all these things here. So from this one, the system transfer function y of z is equal to y of z into 1 plus summation k is equal to 1 to n ak into z power minus k is equal to summation k is equal to 0 to m into bk into z power minus k into x of z. So from this one, the system transfer function h of z is equal to y of z by x of z, so which is equal to the summation k is equal to 0 to m bk into z power minus k divided by 1 plus summation k is equal to 1 to n ak into z power minus k. So clearly observe it here. Just you can expand this one here. B0 plus B1 into Z inverse plus B2 into Z power minus 2 plus up to the plus Bm into Z power minus m divided by 1 plus A1 into Z inverse plus A2 into Z power minus 2 plus up to the An into Z power minus n. So first, for the given difference equation, you can execute in the form of like this one. First we find the system transfer function, then the coefficients b0, a0, b0, b1, b2, bm. First find out the b0, b1, b2 up to the bm and a1, a2 up to the an. Sir, how we can implement? Very simple logic. So go for the difference equation directly. So y of n, we can expand that summation direct expression minus of, clearly observe it, a1 into y of n minus 1 plus a2 into y of n minus 2 plus up to the plus an into y of n minus n plus b naught into x of n plus b1 into x of n minus 1 plus up to the bm into x of n minus m. So clearly observe it, ma. So whatever in the system transfer functions, b naught, b1, b2 up to the bm. Similarly for a1, a2 up to the an are available. The same coefficients are existed here also. Same thing, ma. So you can execute this function with the help of all the three elements, ma. So here n minus n means delay. An into y of n minus 1 is nothing but a scalar multiplication. Here clearly observe it, ma. It is a delay operation, and this is nothing but a scalar multiplication operation, and this is nothing but a addition operation. So all these three operations are combinedly involved here to get the complete output. Simple, okay, na? So now coming to this one, how to implement this one structure. First input x of n. First clearly observe it. b naught into x of n plus b1 into x of n minus 1 plus bm into x of n minus 1. So first ఈ స్ట్రక్చర్ కరెక్ట్గా చూసుకోండి. సో ఇది b naught into x of n plus next b1 into x of n minus 1. So what is the output here? X of n minus 1. So which will be scaled or multiplied by the coefficient b1. Next, similarly for one more time we can delay, we can get the output is here. What is the output here? We obtained x of n minus 1 is delayed by the one more time, that is x of n minus 2, and again which is scaled by, in the expression b2 is available. Clearly observe it. So in similar way, for how many times you can go for? N times. So last one is nothing but a z inverse. Output of this one is nothing but a x of n minus n, and which is scaled by the b x of n minus m, which is scaled by the bm, and it will be given to the previous adder. So this is the input side structure. This is the input side structure. What about the output side? Student. So y of n. So first y of n is delayed by the how many units? 1 unit. So output of this one is nothing but a y of n minus 1. This y of n minus 1 is scaled by how many units? A1 units. Just I rearranging, no? Okay. So this is the y of n. So output is scaled by the one more unit, z inverse. So here y of n minus 1. This one y of n minus 1, which is scaled by the how much values? Minus a1 into y of n minus 1. Clearly observe it here. Minus of. So minus a1 into y of n minus 1. Next is one more time, it is delayed by the delay unit. We can get the answer is easy. Here is y of n minus 2. So which is scaled by the how much value? Minus a2. So this will be added to the output here. So next, this will be continue for till up to the end of the, at the last stage one more delay unit is there. So output of the delay unit is y of n minus n here. The last unit is y of n minus n times, and which is scaled by how much value? Minus an. Okay, this is for previous outputs. Clearly observe it in the expression. So this will be implemented, ma. Minus a1 into y of n minus 1, and minus a2 into y of n minus 2 minus an into y of n minus 1 is implemented, and b0 into x of n, b1 into x of n minus 1, bm x of n minus m is also implemented. But in between these two expressions, there is a one adder is there plus. So nothing but we just connected those two outputs. That's it. This is the direct form 1 structure. So direct form 1 structure is nothing but directly implemented. Whatever the difference equation is there, the difference equation is directly implemented. The drawback of this technique is nothing but a separate delay elements are used for both input and output. A separate delay elements are used for both input and output. Due to that reason, number of delay elements are increases. If the number of delay elements are increases, automatically, what is the problem? If the number of delay elements are increases, the cost of the circuit is also increases. So totally 3 elements are or 3 components are used here. So the structure requires the number of multipliers or simply number of multiplications. How many number of multiplications are required here is m plus n plus 1. This is the order of the input, order of the order of the output, order of the input, order of the output, and plus 1 is nothing but this one b0 into x of n, present input. Next, how many number of adders are required? One adder is reduces, that is nothing but m plus n. Next, and how many memory locations? So how many memory locations are required here? Memory locations are nothing but delay elements or storage elements. Clearly observe it. For m plus n plus 1, this 1 is nothing but output. So m is nothing but for input, n is nothing but for output, and plus 1 is nothing but for final output. This is for present input and past input. This is for past outputs. This is for present output. So these are the number of requirements, computational requirements of the direct form 1 realization. Direct form 1 realization. So the second structure is direct form 2. So just once again I will show the second type. Before we will start the direct form 2 realization, go for the once again go for a direct form 1 realization. So this is the structure. So directly we can implement the difference equation. So if okay, I will move to the next one. So direct form 2 realization. The another form of the direct form 2, another name of the direct form 2 realization is canonic form realization. Canonic form realization. So for this one, very simple logic. The system function y of z is always equal to the system transfer function is h of z. The system transfer function h of z is always equal to the y of z by x of z in z form, which is equal to the summation k is equal to 0 to m bk into z power minus k divided by 1 plus summation k is equal to 1 to n ak into z power minus k. This is the direct form. So now in case of the direct form to just we reducing the number of delay elements. How we reduce the number of delay elements means very simple logic here. So we can implement in terms of the cascaded form. So h of z is equal to y of z by x of z can be written in the form of y of z by w of z. Okay, one intermediate signal you can consider, and w of z by x of z, both are same. So which is equal to the summation k is equal to 0 to m into bk into z power of minus k into 1 by 1 plus summation, sufficient place not There. Same expression in terms of the two functions we can written. So that is summation k is equal to, numerator is separately mentioned, bk into z power minus k into 1 by 1 plus summation k is equal to 1 to n into ak into z power minus k. That's it. So this is for two functions. So from this one, first case, y of z by w of z is equal to, what is the formula? Summation k is equal to 0 to m into bk into z power minus k. So from this one, y of z is equal to w of z into summation k is equal to 1 to n into bk into z power minus k. Just apply the inverse z transformation here. Inverse z transformation here. So y of n is equal to summation k is equal to 1 to n bk into w of z. bk into w of z into z power minus k. I think all of you know the time shifting property here. Y of n minus k is always z transform pair with z power minus k into y of z. So in place of y of z into z power of minus k, you can written y of n minus k. In similar way, in place of w of z into z power of minus k, you can written w of n minus k. So summation k is equal to 1 to n bk into w of n minus k. Just you can expand this one. K is equal to 0 here. So b naught plus b naught into w of n plus b1 into w of n minus 1 plus b2 into w of n minus 2 plus up to the bn into w of n minus n. So this is the output, present output. So you can go for first equation. It is clearly observe it. So now we can split the y of h of z into two parts. Numerator is the one part, denominator is the another part. We can implement these two in series or cascaded form. In series or cascaded form, then automatically we can get the final structure. It's a very which minimizes the complete errors. So now coming to this is the first equation. Similarly, go for the second one. What is the second one? Numerator, denominator. That is w of z by x of z is equal to 1 by 1 plus summation k is equal to 1 to n ak into y of n minus k. So summation k is equal to 1 to n ak into y of n minus k. So that's the numerator is m. Okay, this is the m. Okay, no problem. But we need main concept. There is no deviation in the concept. No problem. Only change in the variables. Okay, now just you can cross multiply these two. So from this one, w of z is equal to cross multiply these two things. After the cross multiplication here, after the cross multiplication, first x of z is equal to w of z plus summation k is equal to 1 to n into ak into y of n minus k. Sorry, not y of n minus k, y of z into, it is the z power minus k actually. According to the concept, it is the z power minus k. Clearly observe it here. Okay, ak into z power of minus k, ak into w of z into z power minus k. Again apply the inverse z transformation and expand the summation. Apply the inverse z transformation and expand the summation. X of n is equal to w of n plus A1 into W of n plus A1 into W of n minus 1 plus A2 into W of n minus 2 plus up to the An into W of n minus n. But we need here W of n is equal to, what is the W of n? X of n minus A1 into W of n minus 1 minus A2 into W of n minus 2 minus up to the minus An into W of n minus n. This is second expression. So W is nothing but here it is the intermediate function. Clearly observe it. In the first expression, W of n is the delayed. In the second expression, W of n is the delayed. One time which is multiplied with the B1, B2 up to the Bm. Second equation which is multiplied by the A1, A2 up to the An. Nothing but a common delay element is used. A common delay element is used for direct form to realization. A common delay element. So how we can the structure means simple, very neat structure. Just implement the two equations. First, x of n, clearly observe it. X of n minus A1 into x of n, A1 into W of first, implement the second expression. Second expression means this one. So here you can assume that intermediate function is W of n. So what is the output of this one? W of n minus 1, which is scaled by the how much value? Minus A1, and it will be added with x of n. Clearly observe it, ma. X of n plus minus A1 into W of n, minus A1 into W of n minus 1. Similarly, one more time we can delayed, that is we can obtain the W of n minus 2, which is scaled by the how much value? Minus A2, which is scaled by the minus A2, and which will be added with the previous value. So here one more adder is there, two input adder like this one. So clearly observe it. This is the structure of the first part. So the first part is over up to the how much values? Last one is minus An. Minus An. So this is about the direct form to realization. In that structure there is a first part. So output of this one is W of n minus n. Second equation is over. Next, in the go for the first equation, B naught into W of n. So this W of n is multiplied with the B naught, and which will be added. Next, B1 into W of n minus 1. This is the B1. So again here one more adder. Okay. Next, similarly B2 into W of n minus 1. Clearly go for your notes. That is a first equation. Directly you can implement it. So B1, B2 up to the, and final structure here W of n minus n, Bm into W of n minus n. So this is the a common delay element is used for realization of the IAR structures or IAR systems by using these three components like adder, delay, and scalar multiplier. So for go for the direct form one, a separate delay elements are used for both input and output, whereas in case of the direct form 2, a common delay element is used for both input as well as output, where B0, B1, B2, Bm are nothing but coefficients of the inputs, and A1, A2, An are nothing but coefficients of the output. So there is no change in the count of the adders, count of the scalar multipliers, only change in the delay element. So the finally it requires actually same number of m plus n plus 1 multipliers, scalar multipliers, and similarly m plus n adders. But what about the memory elements? Maximum of m comma n adders, sorry, delay elements. So maximum of m comma n, because either it may be numerator order or denominator order. So this is about the concept of the direct form to realization. This is the concept of the direct form to realization. So clearly observe it, ma. Direct form 1 is nothing but a directly you can implement the input and output separately. Whereas in the direct form 2, just we can transverse the structures, ma. Clearly observe it, ma. I just observe my mouse movements. This complete Z inverse is transversed, nothing but a, this complete structure is a transverse, ma. Nothing but a, in place of adders are placed here, inverses are placed here. Similarly, you can transverse or reverse the structure. Inverse elements are here and adders are here. So inverse are common for both input and output. Due to this reason, memory requirements are reduces. Whenever the memory requirements are reduces, automatically the cost of the structure is reduces. So in the real time, which structure is preferable? Direct form 2, because of memory requirements are reduces. Clearly observe it in the real time systems also. Whenever you can go for internal memory capacities increases, like RAM size increases, our desktop computers or our laptop computers or our mobile phones, Android mobile phones also, if the RAM size is increases, automatically the cost of the device is increases. By using this type of the structures, you can reducing the memory requirements, and similarly there is no change in the speed of execution. Only change in the requirements of the memory requirements may be reduces here. Okay, this is about the direct form 2 structure. The third structure is a cascaded realization. Cascaded realization. Cascaded realization, nothing but the name itself indicates cascaded or a series form of realization. So here in this case, nothing but a simply that h of z, the system transfer function h of z is divided into the smaller orders, and all the smaller order transfer functions are implemented in cascaded fashion. Each smaller order function is realized by using the direct form 2. So here h1 of z comma h2 of z up and so on are realized by using direct form 2. Direct form 1 is always simple form. Direct form 2 is the some complex form, but which reduces the memory requirement. So that in majority cases we use the direct form 2. Direct form 2. Best example means, suppose if h of z, suppose if h of z is fourth order system, if the h of z is fourth order system, suppose if h of z is fourth order system, so this complete h of z fourth order system is divided into the second order system, one second order, another one is the second order, no problem. Suppose again, sir, chip space is very small, so go for again the second order is converted into the two first orders. Again this one is also converted into the two first orders. Implement all these four first order transfer functions using direct form 2 and connected in cascaded form. So that is the cascaded form of the realization technique. That is called as the cascaded form of the realization technique. The fourth type of the realization is parallel realization. The name itself indicates parallel form realization. Parallel form realization. So nothing but here the first, in case of the parallel form realization, how is I think all of you know this one, how to convert the multiplication into addition. how to convert A dot B is equal to, how we can convert into the A dot B form is always converted into the A plus B form by using the partial fractions method. 1 by AB is always converted into the 1 by A plus 1 by B by using partial fractions method only. So this is the base for parallel realization form technique. This is the base for parallel form of the realization technique. So in case of the parallel form realization, this can be obtained. This can be obtained by performing the partial fractions method. By performing the partial fraction expansion method. Partial fraction expansion method. Partial fraction expansion method. With the help of this partial expansion method only, you can get the h of z, parallel form of realization, like it, that is h of z is equal to some c plus summation k is equal to 1 to n into ck divided by 1 minus p into k into z inverse. So nothing but either it is suppose if it is having fourth order system, that will be converted into the 4 first orders and add all those 4 first order systems. So in this example, generalized example, c plus, not c1 here, c plus c1 by 1 minus p1 into z inverse plus c2 divided by 1 minus p2 z inverse, like this one. This is about the parallel form of realization. So these are the, and again this will be considered as the one function h1 of z, and this will be considered as a second function h2 of z. This is also considered as the h3 of z. All these lower order transfer functions h1 and h2 and h3 and so on are realized by using which realization again? All these functions are realized by using direct form too, because that is the best method. So these are the totally 4 types of the realization techniques are used for realization of the discrete time systems. These are the 4 methods are used for converting, for implementing or realization or physical existence of the IAR systems. One is the direct form 1, direct form 2, cascaded and parallel form. So in case of the direct form, directly you can implement it here like this one. This is for input, this is for output. Here there is a separate delay or storage elements are used for input and output. Due to this reason, number of memory requirements are increases. Whereas in case of the direct form to realization, we use the one intermediate form W of Z or W of N. Based on, with the help of that one, we can commonalize the delay elements or storage devices. So this is the direct form to structure. Next, cascaded form. In case of the cascaded, the name itself indicates series form of realization. First, we can divide all the system transfer function h of z into the smaller orders like h1, h2, h3 and so on. All the h1, h2, h3 and so on are implemented with the help of the direct form to realization, and all are connected in series form. That is a cascaded form of realization. And next is a parallel form of realization is with the help of the partial fraction expansion, we can divide into the smaller parts, and all the smaller parts of realization systems are implemented using the direct form to realization and add all those outputs now. So this is about the concept of the realization of the IAR systems. Okay. So this is about the concept of the realization or implementation of the IAR systems using direct form 1, direct form 2, parallel form and cascaded form. So Okay, so next class we discuss about the realization of the FIR systems and followed by the some problems. Followed by the problems. Majorly, Tuesday we will finish the FIR filter realization along with the problems. Okay, IR and FIR realization problems, where we finish the second chapter. Okay, and Wednesday